Hello and welcome to Defining Lean Six Sigma Green Belt Level. This is part 1 in the series, and we're going to be going over what Lean Six Sigma is. Our training objectives for this lecture is understand Lean Six Sigma, know the difference between what Lean and Six Sigma are so that you can see what they do together as a powerhouse. List the 8 types of waste and provide examples. List some of the characteristics of a Lean Six Sigma project. Understand the correlation between Sigma level, defects per million opportunities, CPK, and percent yield. Know the 5 steps of Lean Six Sigma. List some benefits of Lean Six Sigma. And understand the historical evaluation of Lean Six Sigma. So Lean Six Sigma is a combination of both Lean and Six Sigma principles fused together for the benefit of the company. It uses the statistical analysis tools in Six Sigma with the hands-on Lean practical approach of problem solving fused together using the DMAIC methodology. So define, measure, analyze, improve, and control. Together they act as a powerhouse of improvement. So Lean Six Sigma is a continuous improvement methodology that combines DMAIC process and statistical analysis tools from Six Sigma in order to reduce process variation and improve process control, and couples them with lean manufacturing tools in order to eliminate or significantly reduce the 8 types of waste in the lean value stream. The losses, the waste, the defects, the things that are eating our lunch, the invisible and the visible losses, and promote work standardization and flow. The main objective is to strive towards a zero-loss workplace, a zero-loss factory. The ASQ definition of Lean Six Sigma is that Lean Six Sigma is a fact-based, data-driven philosophy of improvement that values defect prevention through using such things as poka-yokes, standardized work, ensuring that everyone does the same thing the same way every time, over defect detection. So one of the big things is getting away from having to do 100% quality inspection, which costs us a lot of money. And by implementing Lean Six Sigma into our practices, we can prevent defects before they occur. It drives customer satisfaction and bottom line results by reducing variation, waste, and cycle time, while promoting the use of work standardization and flow, thereby creating a competitive advantage. It applies anywhere variation and waste exists, and every employee should be involved. Every employee from top management all the way down to the operator should be involved in adopting, implementing, and moving forward with a continuous improvement program geared at reducing or thereby eliminating waste in the factory. So let's start to understand what Six Sigma is. Six Sigma process is one of the most important metrics in Lean Six Sigma is Sigma. Sigma is actually deviation. It's standard deviation. It's how far our process deviates from the norm. So if we're trying to eliminate all defects within our factory, then we must understand how far the deviation of our process goes. So we want to look at two different operators. We want to see how they compare to each other, and then we want to streamline that process to eliminate the waste within that value process so that we can bring about more value and limit the amount of waste within our environment and in our processes. Sigma is a statistical term that refers to the standard deviation of a process about its mean. And we're going to go more into that because that can be it can sound a little bit more confusing than it really is. But basically, it's if you compare operator A to operator B, how long does operator A take to do a particular task versus operator B? So if we have an 8-hour period, the standard deviation is going to be the difference, comparing the difference about operator A does it 10 times, then what is the average time for that operator to do it? And then of that, so that's the mean, then of that, how does each one of those instances that we took, so out of the 10, how do each one of those examples vary above the mean? So is it one day the operator is doing a task in 8 minutes, and then another time he's doing it 3, while the average is 4? So you would look at that and you want to see how many times does that 10 spots go on the graph. And then you can make your histogram, which then shows you how the deviation or the dispersion goes against the mean. And you'll start to see what it means. Okay. So let's go to the next. So here we are. Okay. In hypothesis testing, which is the measure of dispersion, we use the standard deviation to describe the shape of the curve. And so let's look at that. A sample that has a large standard deviation, so this one here, you see how it's going towards, it's hugging and being pulled, right? So it's being really, really pulled at both ends so that it starts to flatten out that curve and then just spread out, kind of like a blob. So a sample that has a larger standard deviation will be fatter, okay, because those extreme outliers, that 8 minutes versus the 3 minutes, are really tugging against that mean of 4 minutes that we had talked about earlier. And it's not the average here. So a sample that has the fatter and shorter than one that has a smaller deviation. So here we have the smaller deviation, okay? The Q1 has a smaller deviation because operator B, let's call him operator B, tends to do it either between, so his average is 5 minutes. He tends to do it at 5.5 minutes and or 6.5 minutes. So he's pretty tight in comparison to the operator who's doing it 8 minutes to 3 minutes. So you can see that his operator A is going to be stretched, and there's going to be a lot more data spread out as 8 is far away from 3 versus the other operator B. Okay, so standard deviation, again, describes the shape of the curve. So if we have a smaller standard deviation, it's going to be tighter and the peak is going to be taller, okay? And if we have a larger standard deviation, it's going to be fatter and the peak will be shorter. So let's describe the two important elements of a bell-shaped curve, which is the normal-shaped curve. This is the whole premise behind statistical analysis. So if we can understand the bell-shaped curve and whether it's normal or not normal, we're going to go a long way into understanding those models when applying them to inferential statistics. So two important measures in Lean Six Sigma are the mean. The mean measure is the measure of the central tendency, which is denoted by the mean. And the mean provides the position. So the position is critical. Where this position is going to be the biggest factor in the type of statistics that you do, whether they're non-parametric or they're parametric. We're going to dig deep into that so that you truly understand that it is this shape here of your data distribution that tells you what kind of statistics you have to apply in order to get an accurate model. Because remember, statistics is just a model. It's just applying a bunch of data and coming up with a model and identifying if our data and our model coincide. Do they agree or do they disagree? And this is the reason we have to often repeat statistical analysis on different sets of data. So the mean may be defined as the average value out of a data set, whereas the standard deviation is the measure of central dispersion, which is denoted by the standard deviation. The standard deviation provides the shape, how fat or how thin this is, how high the peak is. So here, the shape is going to be really tight because all the data is hugged together in the middle near the mean. If it was a low-shaped curve, then that means that there are outliers in your data set that are pulling the distribution out further than is normal. Then to a certain degree, it would become a non-normal distribution. And the standard deviation may be defined as the average distance any point is from the mean of a data set. The average of the averages. So let's look at a normal curve. The normal curve fits the 68, 96, 99.7 rule, which means that plus or minus 1 standard deviation is going to fit 68% of the population of your data set. It's going to fit within this area of 1 plus or minus 1 sigma. Then plus or minus 2 sigma is going to be 96% of your data set, which is actually 95.4. We're going to have here to here. This is where 96% of your data set is going to fit. And then plus or minus 3 sigma here is where 99.7% of your data will fall. Anything that exceeds plus or minus 3 sigma from this is considered an outlier. And it would be here or here. And in that case, your data set is non-normal and you cannot apply the normal distribution curve to your data set. That is when we're going to use non-parametric data. Okay. Six Sigma process. Sigma is used as a scale or a metric to measure the variation in the process. The tighter the variation, the higher the quality of the process, because all of your data is hugging together. A process is said to be a Six Sigma process if 6 standard deviations can fit between each side of the process. So each side of the process, average, and the customer specifications. This equates to a CPK of 2.0. And more about CPK later. Note, applies only to a normal process, one free of special cause. That right there is key. And what that's saying that is, if it's a non-normal process, we're going to have to apply non-parametric testing. For hypothesis, that is the Moods median test or the Crusoe-Wallace test, and we'll get into more on which one you're going to want to apply. And we're going to stop our video here, and because YouTube only allows 15 minutes. And we will pick up next time, starting with DPU, DPMO, and DPO. Thank you.
This concludes this video. Please join us by subscribing to our YouTube channel or at lean6sigmaprowess.com for more training content. Thank you.